Hi, welcome back. We have been talking for quite a while about the continuous time Fourier transform, and that is just evidence of how important the CTFT is to engineering and how wide-ranging its applications are. I have one more video for you regarding how frequency responses of different systems in different arrangements like parallel or series or cascaded combine to make an overall frequency response, because it's often not the case where you just have one system. If you're thinking in terms of circuits, you might have a circuit that does one thing and then that's connected to a circuit that does another thing. So we might be interested in how do the frequency responses combine in the overall system. So that's what I have here for you. Let's get started. Now, again, I want to remind you, this is the big picture really. This is the engineering picture. It's easy to get lost in the mathematics, but force yourself not to get lost in the mathematics and to come up for, a breath of fresh air and get the engineering part of this. A linear time invariant system will have an impulse response and a frequency response, and those two things are Fourier transform pairs. When I put a signal x in, I get out a signal y that is the convolution of x with h. But according to the convolution property of continuous time Fourier transforms, the spectrum of y is the multiplication of capital X with capital H. So this gives me two choices. I can either perform convolution to get the output, or I can perform multiplication in frequency to get the output. What happens when I have two systems? And in particular, I'm interested in their frequency response because that's what we've been talking about for quite some time. So let's say I have a system here that's first, and we'll say it's linear time invariant, and it has a frequency response capital H1 of j omega, and the second system is also linear time invariant, and it has frequency response H2 of j omega. This is a common case, especially in circuit analysis. You have one circuit that does something, and then you feed that into a second circuit that does something else, and you want to know the output of the cascaded arrangement or the series arrangement. So let's try to understand what happens here. Well, x has Fourier transform capital X. That makes the, if you want to call this W of t, that makes the spectrum here x times h1, right? The spectrum of the output is the spectrum of the input times the frequency response. Okay, now this thing becomes the input to the second system. So now the Fourier transform here, this is ft, Fourier transform here, y of j omega is equal to the spectrum of the input, right, times its frequency response. I'm running out of space here, so I'm going to put this down below. So we just applied that principle twice. But what is W? W is x times h1. So we can write this as x of j omega times h1 of j omega, that's W of j omega, and then times h2 of j omega. So if we remember that the overall frequency response of a system is y of j omega over x of j omega, right? Solve that for h. Then we get the frequency response of the overall system is h1 of j omega times h2 of j omega, and we'll just call that h. So we conclude that the frequency response is the multiplication. So if I look at this as just one circuit now, one box where x goes into the box and y comes out of the box, the frequency response of that one box in green is the multiplication of the individual frequency responses. That's pretty cool. All right, now let's consider a parallel case. So let's say we have x of t coming in, right? And then we have a linear time invariant system, h1 of j omega there, and a linear time invariant system, h2 of j omega here, and then their outputs are added together to get the total output. So we might call this guy, this intermediate signal, W1. We might call this guy W2. We're interested now in what is the overall frequency response of this situation or this circuit. So I'm going to erase this thing, and I'm going to erase this guy. Again, feel free to pause the video. All right, so W1, at least its spectrum, j omega, is going to be x of j omega, so x's spectrum, times the frequency response. W2, similarly, is going to be x of j omega times the frequency response. Okay, then W1 gets added together. So we have y of t is equal to W1 with added together with W2. So what's the transform of that? Well, the transform of the left is capital Y, and then using linearity, we can take the transform of each piece separately. So this is W1 of j omega, excuse me, plus W2 of j omega. Okay, well, what is that? Well, we have them up here. This is x of j omega times h1 of j omega plus x of j omega times h2 of j omega. And so we can factor out the x, right? And we get h1 of j omega plus h2 of j omega. And then, remembering that the overall frequency response is y over x, I can divide by x, and I get the overall frequency response is h1 plus h2. I'll call that h. So, if I just looked at my situation as one circuit, x goes into the box, one box, x goes into the box, y comes out of the box. What's the frequency response of the box? It's the individual frequency responses added together. So now with those two results, the one that I erased, the cascaded arrangement, and with this you can build up higher blocks, right? You can have another parallel a series block here, and then that's in parallel here, and you can imagine how we can start, building more and more boxes, more and more circuits, more and more systems, and we can figure out what the overall frequency response of the system is. All right, so that's all I have for you for continuous time Fourier transform. So now we're going to shift our attention to discrete time Fourier transform, and because we covered the continuous time in such detail, we won't need to cover the discrete time Fourier transform in as much detail, but there are some little fine points that we need to hit that are specific for discrete time. So I will see you in the next video.